Okay, we're back here. We're looking at the p-series special class um, of functions, and I realized I made a mistake at the end of the video. I was rushing to fit into the 15-minute confines of YouTube. So let me just erase this. And what we were doing is we were integrating um, 1 over x to the p, and we were integrating it uh, in particular for p not equal to 1. If we were integrating for p equals 1, if we were looking at when p equals 1, the integral of 1 over x to the p when p equals 1, that's easy. That's just, and we're going from 1 to t. That's just ln of x from 1 to t, which is just ln of t minus ln of 1, which we know is just ln of t. And that's where this comes from. Um, but where I got stuck before, I just plugged things into the wrong place. Um, if if we're integrating from 1 to t, 1 over xp dx, uh, we use the reverse power rule. We get x to the negative p plus 1, the negative because the p is in the denominator, over negative p plus 1, and that's to accommodate when we use the power rule to ensure that we get a coefficient of 1. So you're familiar with that sort of integration. But then we need to evaluate for t and 1, and we're evaluating into x, and that's where I made the mistake before. So this should be t to the negative p plus 1 over p plus 1. Uh, Minus, putting in 1 to the negative p plus 1 all over negative p plus 1. And this simplifies to t to the negative p plus 1 minus 1 all over negative p, not negative, yeah, negative p plus 1. And that's where this came from, right here. And that's when p doesn't equal 1. And then the idea is when is it convergent and when is it divergent? Well, the key thing to look at in terms of convergence and divergence is to look right in here. And, you know, as long as p is bigger than 1, for p bigger than 1, as long as p is bigger than 1, um, this this t to the negative p plus 1 will be t raised to a negative number. So as long as p is greater than 1, then this red box is going to be t raised to a negative number. And if it's t raised to a negative number, as t gets huge, as t approaches infinity, infinity raised to a huge number is just 0. And what we'll get left with is just this negative 1 over negative p plus 1. So for it to converge, p must be greater than 1. If p is less than 1, if p is less than or equal to 1, uh, then then t will remain essentially in the numerator. If p was equal to 1, then we just have t minus 1 over negative p plus 1. As t gets close to infinity, the whole thing does. If p were bigger than 1, then we'd be squaring or cubing or whatever some huge number t. So the p-series test, if you have anything following something like this, we know it's going to be convergent as long as p is greater than 1, divergent if it's less than or equal to 1. And if you need sort of more proof of that, I think the easiest thing to do would be like, let's look at two cases. And I think those cases are coming up right now, right here. And I'm gonna do the use our p-series test and then show the integration so that you can really sort of see why. So um, determine whether the following series converge or diverge. Well, we know that we could rewrite this as 1 over n to the 1/2, and this is 1 over n to the 3/2. And what we need to look at, so here our p-value is 1/2, here my p-value equals 3/2. And if I just go back a slide, our p-test, if p is greater than 1, it converges, and if it's less than 1, it diverges. So here, 1/2 is less than 1, so this is going to diverge, and here 3/2 is greater than 1, so my function will converge. But let's really sort of let's take the time to really see why, because I think once given a concrete example, you're gonna be like, oh yes, 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 of course. So we're thinking about the integral from 1 to t, where we're letting t get close to infinity, of 1 over x to the 3/2 dx. Well, um, this is the limit as t approaches infinity. And just to rewrite this, this is x to the negative 3/2 dx. Okay, well now let's do the integration. We're adding 1, so this becomes x to the negative 1/2, and then over negative 1/2, so that we keep the coefficient of 1, integrated from 1 to t. And now, when I evaluate, I'm going to get t to the negative 1/2, -2, simplifying this, minus, so minus -2 times 1 to the negative 1/2. And as t gets huge, we're looking at t values get, the limit as t approaches infinity. Well, as t approaches infinity, t to the negative 1/2 is going to be 0, and then plus 2 equals 2. So we're converging to a single number of 2. And the idea being, as long as your p-value, 3/2, and here it became negative 3/2. As long as that value is more than 1, when we integrate, as long as this value is more than 1, when you integrate, it's going to integrate to a negative exponent. And the fact that it integrates to a negative exponent means that when we let t get toward infinity, it's going to be infinity raised to a negative exponent, which is going to make that go away. Whereas on the other example, on the first one, to the 1/2, just to make sure we sort of see, why does one converge and why does one diverge. If we look at this example and take the time to actually do the integration, we're looking at the integral from 1 to t, where we're letting the limit as t approaches infinity of 1 over x to the 1/2 dx, and that equals the limit as t approaches infinity of the integral from 1 to t of x to the negative 1/2 dx. And now, because that p-value, the 1/2, is less than 1, when we integrate, we're adding 1 to that power. When we add 1 to that power via our integration, when we integrate, we're going to get x to the 1/2, 2. 2x to the 1/2 from 1 to t. And now, because my power was so small, because my power was less than 1, I no longer have a negative exponent. So when I evaluate this, when I look at this, I'm going to get the limit as t approaches infinity of 2 times t to the 1/2 minus 2. And as t gets close to infinity, this value is going to blow up and the whole thing diverges. So you can memorize this rule, and in fact, it's worth memorizing this rule. What rule? This rule back here, for p-series tests and convergence and divergence. But recognize that there's a reason why. The reason why is, when p is greater than 1 and we integrate, we're still going to have a negative exponent, which is going to make something converge. Whereas if p is less than 1 and we add 1 to integrate, now we're going to have a positive exponent. Positive exponent is going to cause divergence. So that's where this test here comes from. But now we're going to get into alternating series. Previously we were looking just at non-negative values, looking at non-negative sequences in series and determining whether or not they converge or diverge. Now we're going to look at alternating series. So we're going to have, this feature -1 to the n plus 1 or -1 to the n, which is going to cause my signs to oscillate, negative to positive to negative to positive. Um, and we're going to figure out how to determine whether those converge or diverge. Um, but that's going to be for the next night. So we're going to end with these two videos, and we'll look at alternating series in a little bit.